Okay, let's start recording. Fine. Okay, so team, so what did we cover in the last session?
Binary trees.
Binary trees, right? Different types of trees, a lot of concepts, and then we started looking into binary search trees. There we said that all the keys in the left subtree of a node is less than the key of that node, and all the keys in the right subtree of a node is greater than the key of that node. So that was a special property of binary search trees. And we covered insert, search, and we were looking at the delete function, right? And in all the three functions, we saw that the worst case complexity can be n, right? In the worst case, if we have a skewed binary search tree, right? You can write a simple example for a skewed binary search tree. The worst case complexity for search or insert or delete can be n. Okay, so it is important. Right. We were looking at the delete function. Let's start with this. So we said there were 4 cases. These 3 cases are simple, right? We have to cover the 4th case. What is the 4th case? We want to delete a node, and the node is found, the key is found, and it has 2 non-empty children. How do you delete that node? Because if there is only one non-empty child, it is very easy. That becomes the parent, right? That occupies the location of that node. But if it has 2 non-empty children, right, maybe something like this, then what happens? So who will succeed, right? So that's the scenario. So the idea here that we will see is, suppose you want to delete this node, okay? Suppose you want to delete this node. So you have the left subtree, you have the right subtree. You want to delete this node, and it has 2 non-empty children. This is non-empty, this is non-empty, right? Both the subtrees are non-empty. What do? The first thing you need to do is find the predecessor of the node. So what do you mean by predecessor and successor? So we know that if we do an in-order traversal of the entire tree, right, you see that this list will be in sorted order, right? An in-order traversal of a binary search tree will be in sorted order. So what is predecessor of a node with key say 75? It is the node that is immediately left of 75 in this sorted list, right? Suppose you get a sorted list of all the numbers in this BST. What is the predecessor? Suppose 73 is the maximum valued key, just less than 75, then 75 is the predecessor, and say 83 is the successor. That means between 75 and 83, there are no other numbers. Between 73 and 75, there are no other numbers, right? So we call 73 as the predecessor of 75. We call 83 as the successor of 75. So here we will just care about the predecessor. So we find the predecessor, locate the predecessor of the node that you want to delete. And where will that predecessor be? Where will that be located? So we can find the exact location of predecessor by using this template. Current dot left dot right. What is the meaning of this? So this is your current node that you want to delete, right? Current dot left is this node. Current dot left is this node, okay, that I'm highlighting here. And then keep going right child of this, right child of this, right child of this. The claim is that this node right? Suppose this is the dead end, you cannot go further. And we don't care about that null nodes and all, right? So suppose this is the non-null node that you get if you go to the left of the current node and then keep going right until the dead end. This will be the predecessor of current, right? Cur dot left dot right will give you the predecessor of the current node that you want to delete. Now, what do? Predecessor will take the location of the node. Say, suppose you want to delete this current, the value of predecessor, right? The value of predecessor will go here. Suppose you wanted to delete 75, right? And so you have this left subtree, right subtree, and the predecessor, maybe this is, say, 73. 73 is found here. And no other node in this left subtree is greater than 73 and less than 75. So this is really the predecessor. So 73 will come here, will take the location of the node, right? So it will come here. And then what do? So this becomes 73, right? Then what do? You recursively delete this 73 from the left subtree, right? You recursively delete the predecessor from the left subtree. Okay, makes sense? See, we deleted 75 really. 75 is out. We deleted 75. In place of 75, 73 comes in, and we delete, because now there are two copies, right? 73 is here also, and 73 has been copied here also. So now we need to delete one copy. So we will delete 73 from this left subtree. Okay, makes sense? So that's how the delete works in this fourth case, which is the most complicated case here.
Professor, is there a question?
Yes.
Hello?
Yes. Shoot. Yeah, so yeah, please ask the questions. Okay, I think there was a call drop. So let's start with an example, right? It will be easier to understand with an example. And feel free to ask questions if you have, right?
Professor, I have a question.
Yes.
Okay, do you mind just go back to that slide?
Right. Okay. This one.
Yeah, so here you said that predecessors left children will take the location of the predecessor, right?
Right. So here, when we say this, we are just copying the value.
Understand. But what I think in this case, the predecessor does not have a right child, right?
Yes, it does not have a right child. Correct.
Okay, that's my question. Thank you.
Right.
Okay, but they could have a left child because
yes.
Okay, I see, got you.
It may have a left child, it may not have a left child. I mean, in either case, if it does not has a, see, left child, you can say it always exists, right? If it exists, it can be a null node or a non-null.
Yes.
And it doesn't matter.
Yes.
Right? It doesn't matter.
Mm-hmm.
Okay, so this is the most complicated case, right? We want to delete a node and it has two non-empty children. Suppose you want to delete 88. 88 has two non-empty children. So what do? The first thing, right? You search for 88, right? We said search is so important that search is the core functionality in insert, core logic of insert. And it is the first part of the logic of delete as well. So you have to definitely search for 88. It is found. Now you want to delete 88. What do? The first step, find the predecessor. How do you find the predecessor? So go to the left of 88 once, just once, and then keep going right, keep going right until the dead end. Of course, here we cannot show more nodes, but if there were, right, if there was a right child of 82, we could have gone there as well, right? Until you hit the dead end. So we found the dead end here, 82. There is no non-empty right child of 82. So we stop. So this was the current node. Now this is our predecessor of the current node, 82, right? Now you can clearly see that there is no number that is less than 88 and that is greater than 82. So 82 is definitely the predecessor. Okay. Now what do you do? So once the first step here was finding the predecessor. Okay. We found the predecessor. Next, copy the predecessor. See, 82, you copied the predecessor here. Instead of 88, now this became 82. Right? And what else did we do? We copied it here. I mean, there was, so one step is skipped here in the diagram. 82 is still present in the left subtree, right? We delete that. We delete 82 from here recursively. We recursively delete 82 from here, right? Because you don't need to touch any of these parts. Outside parts, you don't need to touch. That's fixed now. So you go deeper and delete 82. And
Professor,
again,
can I
yes,
ask a quick question? Can you go up a slide?
yes. This one.
Yeah. So instead of, before we copy 82 to 88, can we just set 65's right child to 82's left child instead of recursively deleting? Can we just move, 65 so it points to 76?
Yes.
Isn't that okay?
Right. So what you're saying is 76 is the left child of 82, right?
Correct.
Why don't we push the left child of 82 as the right child of 65?
Yes, instead of just like recursively deleting it, isn't it easier just to shift that?
Right. That essentially, that's what happens.
Okay.
Right. Essentially, that's what happens. Right. But, I'm trying to explain the logic, how that happens. See,
Right, but
you
I guess what
know
I'm saying
that
is, do we
80
have to do it recursively? I guess is what I'm asking. Or
right.
is it, oh, okay.
So when you call that recursively, right, in the next level, what happens? See, if one node has only one child, what happens?
Oh, I see. You're just calling delete again and get. I got it now. Thank you.
Right, you're just calling the same function, right? Yes, maybe you can optimize here and there without calling that, but maybe it is easier if you think about this recursion, because the conceptually, right, it is easier to visualize and stuff.
Yeah, I see it. Thank you.
Right. Okay. Yes, essentially that's what happens, right? 76 goes up and sits as the right child of 65, right? 88 was deleted and that redundant copy 82 was also deleted. I mean, 82 was copied first, right? So the other copy was deleted. So essentially you're pushing 76 up. See, that's what is given here. See, when we write like this, we are saying that predecessor's left child will take the location of the predecessor. Right? What was predecessor's left child? 76. 76 took the location of 82. Right?
Oh, I see.
Essentially, that's what is happening.
Okay.
Okay. Now let's look at the code. We want to understand the code, right? I think we have scanned all these. Did we scan all this? This is just the search logic. No big deal. Search logic. search logic, right? So we
Yes.
don't need to repeat this again because we have seen this multiple times. Suppose we find the node that we want to delete. Here is the big question, right? What is the logic of delete? This is the logic of delete logic. This is the delete logic. So hence I have shown it using these dots, right? These lines. This is the delete logic. Okay. Now let's see. If current dot left is equal to null, so what that means is, so this is null. This may or may not be null. Right side may or may not be null. So in that case, just do current is equal to current dot right. Current is equal to current dot right. Right? So that's the meaning of this. So you deleted it. Okay, this is simple. So if it has 0 child or 1 child case, I mean part of 1 child case, that is covered here. So if current dot right, else if current dot right is equal to null, so which case is covered here? Current dot right is equal to null. This is null, but this is not null. Then what do you do? Current is equal to current dot left.
Professor, I think here this case has been covered in the first number, not 8, right? Because if is now, right? You got, oh, okay. I'm sorry. Take it back. Sorry.
Yeah, I mean, it covers part of the logic, right? Not completely. Okay, now the most difficult case. Which case is this? Left
Two children.
is non-null, right is non-null, right? This is the most difficult case. That means we are dealing with 2 child nodes to a node that we want to delete. Most complicated case. So what do? We find the predecessor, right? First step is find the predecessor. What is the predecessor? Go left once and keep going right until the dead end. That's what we will do, right? So keep going, I mean, go left once, and keep going right until the dead end. What do you mean by keep going right? You can say that I want to find the max element in the left subtree, right? That's the meaning of it. Go to the left subtree and find the max element in it. Isn't it? This is the meaning of finding the predecessor. So here I will not show you how to find max, right? It's just going right of every node you see. I mean, so you start with the current node, go to the right of this. And then you get another node, go to the right of it until you hit the dead end, right? So find max, suppose that returns a node, then you do dot key. You just want the value of that, right? So you found the predecessor value. You copy that predecessor value to current dot key, right? Suppose, so what was the value? So it was 82 or something like that, right? Now you copied that 82 here. 88 was replaced with 82 now, right? Okay, then what do you do? Delete of current dot left, current dot key. So what is the meaning of this? So you have 82 now, 82 appears twice, right? So this is okay, this has been fixed. Now you consider the left subtree. This is the left subtree, current dot left is the left subtree. Current dot key is 82, right? Because the current dot key is 82 now. So in this left subtree, delete 82 or delete current dot key, right? What is this delete? This is a recursive delete. This is a delete function and we are in the logic of delete function. So this is a recursive call. What are we deleting? We are deleting what is current dot key. What is current dot key? It is the predecessor. So we are recursively deleting the predecessor from the left subtree. Make sense? And what do we get? Once we delete, we get the new root. That will be current dot left, right? So after deleting 82 from this left subtree, you get the root of that subtree, new root. That should be the left child of 82, right? So current dot left is the new root after deleting the predecessor from the left subtree. Make sense? Find predecessor, delete predecessor. Done. But of course, I mean, we can show multiple steps also, but core logic, find predecessor, delete predecessor. Okay. So is this clear?
Yes.
See, this recursive delete doesn't mean this delete will be called hundreds of times, right? So depending on the cases, one of these cases will be quickly called. This zero cases, I mean, zero child case, or one child case, two children case will be called once. Make sense? Okay. So see, try to understand this logic from this example, right? It is very easy. So 82 was the predecessor. You are copying 82 to the node value 88. 88 is replaced by 82 now. And then you recursively delete 82 from the, 65 subtree. See, once you delete 82 from 65 subtree, this is what you get. Okay, makes sense? So this is the core logic, right? Descriptive logic and the pseudocode. So this is descriptive logic. This is pseudocode. So I have a question here. We chose to use predecessor. When we delete an item, say 100, the predecessor of 100 will replace 100. What if we change the logic to the successor will take the position of the deleted node? So if we change the logic from predecessor to successor, will it work? What do you think?
Can you go to the slide that shows a tree so we can look at it?
Yes.
Yeah, thank you.
I think it will work.
It works.
I think, but probably all the logic has to be changed.
But no, it doesn't work because if you change it with the successor, then 65 is going to be greater than 44 and it'll be on its left.
Okay, so is it possible to make it work?
Yeah, but the total logic has to be changed. That's what I think.
Okay, so right. So see, exact detail, it's not that you're replacing predecessor with successor and everything remains the same. There might be slight variations here. Instead of the left child, it can be right child and ... But you can write a very similar code with the successor as well. Right? Very similar, very similar. Instead of right, you might choose, instead of left, you might choose right and ...
Oh, I see. Okay.
Right? Yes. So that means we chose predecessor here. That's fine. One could have written the code with replacing the node with successor also, right? Because it is symmetric, right? It is
Yes.
symmetric. So if we can use predecessor, we should be able to use successor and write a very similar logic. Instead of find max, it can be find min, right?
Yeah. Yes. That's
Current
right. Yeah.
dot left, it can be current dot right. Very similar. Okay. Okay. Next. This is a recursive algorithm, right? So try to think of writing an iterative algorithm, non-recursive algorithm for deleting an item in a binary search tree, right? This is a good exercise. So try to do this, right? Analysis. Analysis O of H, right? It should be O of H, which is O of N. In the worst case, right? If you are given a tree like this, 10, 20, 30, right? So on. This is a skewed tree. Of course, it takes n time just to scan, right? Go to the bottom of this tree, right? You have to take, n time, right? So in the worst case, the search, insert, and delete time complexity is n, right? So you see that the search, insert, and delete complexity for binary search tree is O of n. O of n, right? So we are done with BST, right? Binary search tree. Now we will move to balanced search trees.
I have a quick question actually on that last slide.
Yes.
So, my viewpoint or my view of binary search trees have been that, if you have like a perfect tree that has n elements, the
Mhm.
height is the log of n, and so to traverse down to h, that would be log of n.
Mhm.
Are we saying that it's O of n because in the case that you just get a tree that is actually just a singly linked list, then it would technically be O of n?
Correct. So as
Okay.
we discussed in algorithm analysis, right? Whenever we talk about time complexity, we typically cover the worst case, right? But
Yeah.
perfect tree is the best case here. It's not the worst case, it's the best case. Best case is log n, right? If the tree itself is a perfect tree, then the worst time complexity for that particular tree is log n. But it
Nice.
doesn't mean the tree itself will be in that format all the time,
I see.
right?
Okay. Yep.
So we always cover the worst possible data distribution, the worst possible operation, right? So on.
Yeah,
And-
I was kind of in my mind, I was kind of comparing it to like a binary search of an array, but it's not the same.
right. Though the logic of searching is very similar to binary search, right? And so that's why it is also called a binary search tree, right? But as you can see, if the tree itself is skewed, it does not divide the data into two equal parts, right? 10, 20, 30, so on. Suppose you're searching for whatever, 100. Then you go here. What is the reduction? This was anyway null pointer, null pointer, null pointer, right? The reduction is from n nodes to n minus 1 nodes. Reduction is from n minus 1 nodes to n minus 2 nodes, so on. We are not reducing the problem size by a factor of 2.
I
Right?
see. Yep.
So this is the best case. This is the worst case. And we care for the worst case.
Yep. Thank you.
Okay.
Professor, I have a question. Do
Huh.
you mind just go back to slide 61?
61. Yes.
Yeah, this one. Okay. Very simple question. Now look at the root is 44, right?
Right.
Then you go down, so underneath you have 54. Is that possible? I mean, say here, you say 29, right? So if we move 44 to the right leaf, the right child of 29, move up the 54 to replace the place of 54, it is still a binary search tree, right?
Correct. See, given okay, let me show you one example here. Suppose we consider 1, 2, 3, right? The
Yeah.
numbers 1, 2, 3.
Okay.
Write all types of binary search trees possible from 1 to 3. See, 1, 2, 3.
Okay, yes.
1, 2, 3.
Okay. 3,
Then-
2, 1.
1, 2, 3.
Yeah,
right?
yeah, like this. Yeah.
And what
okay.
else? I mean, are there more?
Yes. Probably that's it.
I don't know. So try to think about this. Are there more? And similarly, see, this is a good algorithmic question to ponder upon. I give you numbers 1, 2, 3, so on up to n. You tell me how many
Number of.
BSTs are possible.
Okay.
How many
Gotcha,
BSTs
gotcha.
are possible using these numbers? Right? So that's a good exercise.
Okay.
Yeah,
So-
this is not the only way to arrange this, I mean, these numbers.
Okay, okay, I got you. But probably this is because of the order when you input those nodes.
Correct. See, if you keep inputting 10, 20, 30, what happens? 10 will be put first, 20 will be put next, 30 will be put, right, as the
Yes.
third one. But if you input 20, 10, 30, then what happens? 20 will be here, 10 will be here, 30 will be here.
Yeah, yeah, got you. Thank you very much.
Okay. Okay, let's move to balanced search tree, right? So we learned binary search tree as kind of the basics. That's not even the takeaway, right? So those are the foundations for really this balanced search trees. And this is fantastic. This is amazing, right? Let's see. Why do we care for balanced search trees? See, we want to balance. What do you mean by balancing? We want to ensure the time complexity is log n for all the 3 operations, right? We said it is best case, right? We want to achieve that best case in the worst case also, right? That is our aim. So if our aim is to have log n complexity everywhere for all these 3 operations, what does that mean? We need to construct a tree such that the height itself is kind of approximately log n, right? Theta of log n. Okay, if the height is theta of log n, what does that mean? Maybe after every insert operation or after every delete operation, we adjust the trees such that the height is kept as, theta of log n, right? So we need to do some balancing act after insert and after delete. Search anyway doesn't change the data structure. It is only accessing, right? What is changing the data structure is insert and delete. So what we need to do is after insert and delete, we want to reorder or balance it, right? Such that the height remains theta of log n. I mean, that is the core idea behind all implementations of balanced search trees. Okay, so amazingly, we can get this complexity. And whenever you use tree set, right? Tree set in your programming languages, maybe there are other words in Python and other languages. In Java, this is called tree set. A tree set is a balanced search tree. By default, I think in most packages, it uses red-black trees for the implementation of balanced search trees. But here, we will learn 2-4 trees, okay? Because this is very simple to understand, simple to visualize. We will learn 2-4 trees, but we will still get the same complexity, okay? So the difference between red-black, AVL trees, 2-4 trees, scapegoat trees, ... is majorly in the probably in the performance, right? Runtime performance. Theoretical complexity will be log n for all these 3 operations. Okay, let's start with 2-4 trees. So what are 2-4 trees? So 2-4 trees, also called 2-3-4 trees, is a balanced search tree. Okay, so it satisfies 2 properties. Look at this: size property and depth property. What does size property mean here? Every node, every non-empty node, I mean, typically when we say node, let's assume that we mean non-empty. Every node has 2 or 3 or 4 children. This is important. 2, 3, 4 comes from this. 2 children, a node can have 3 children, or a node can have 4 children. And depth property, all empty nodes, right? Null nodes have the same depth. So here is one example. Look at this. It looks like a binary search tree, right? But this is not binary. Well, look at the branch factor. It has 2 children, 3 children, 4 children, 3 children, 2 children, right? 3, 2, 2. So the number of children each node can have is 2 or 3 or 4, right? It shouldn't be anything else. Okay, what else? If it has 2 children, it has 1 key. If it has 3 children, it has 2 keys. If it has 4 children, it has 3 keys. I mean, similarly everywhere else, right? Okay, what about the depth property? All empty nodes have the same depth. What do you mean by this? These are the empty nodes. They are at the same level, depth. Simple, right? Okay, so these are 2, 4 trees. What else? So here is another observation. This is like your binary search trees. Look at this 5, 4. All the keys to the left of this node have values less than 5. All the values to the right of this node, right child, right? They have values greater than 10 here. Okay, and all the values between 5 and 10 are present here in the middle child. So similarly, so all nodes to the left of 12 are less than 12. This is greater than 12, right? So less than 15, but greater than 12. Okay, next, greater than 15, so on. Okay. So there are 3 types of nodes: 2 nodes, 3 nodes, 4 nodes. As discussed, I node. I node will have I children, right? I can be 2 or 3 or 4. If it has I children, it will have I minus 1 keys, right? 3 children means 2 keys, 4 children means 3 keys. Make sense? So here is this is the example. 6, 7, 8 is a 4 node. 3, 4 is a 3 node. Then what else? 17 is a 2 node. Okay, only 3 types of nodes. Now let's look at the 3 operations: search, insert, delete. Suppose you're searching for 24. So how do you search? Very similar to your binary search tree. Okay, 24 is greater than 22, so go right. 24 is less than 25, so go left. In every node, search all the keys. There are 2 keys here, so search all the keys. So 23, 24, 24 is present. Done. Make sense? So this is similar to your binary search tree with some variants. Each node can have multiple keys, and there is also a middle child node, and so on. Right? Now, look at this. Is this a 2-4 tree? Can you tell me, is this a 2-4 tree?
No,
No.
Why not?
level.
Right. It does not satisfy the depth property. Right? Good.
Yeah.
Next. 12. So if you're searching for 12, let's see. 12 is less than 22, so go left. 12 is greater than, okay, 12 does not appear here or here. And 12 is greater than 10, so go right. So 12 does not appear here, but it's less than, go left. So 12 does not appear in 11 and 13, but it is between 11 and 13. So go through the middle node and you hit the null node. That means 12 does not exist. Right? Simple, like in your binary search tree. Now let's look at the insert operation. So this is your 2-4 tree. You see that the size property as well as the depth properties are satisfied. So only two properties, right? What you need to make sure is these properties are satisfied after every operation. See, these are invariants. The size property and depth properties are invariants. They should be satisfied after every operation. Search anyway does not change the data structure. After insert and delete, you need to make sure these properties are satisfied. Why should we care for these properties? Because if we keep these properties invariants, that these two properties can be used to prove that the time complexity is log n in the worst case. Theta log n in the worst case, or you can say O of log n, right, in the generic case. So these variants are helpful. I mean, every balanced search tree, right, will have its own variants. Red-black trees might have its own variants. Scapegoat trees might have its own variants. Not variants, invariants, right? So for 2-4 trees, the invariants are size and depth property. Okay, fine. Suppose we are adding 17. Where will that go? So before inserting, you want to find the location. For that, you need to apply search. Okay, search for 17. What happens? So 17 does not occur here. 17 is greater than 12, so go to the right. So 17 does not occur anywhere here, so insert 17. Okay, so once you add 17 to a leaf node, right? I mean, these are leaf nodes, right? We can consider all these are leaf nodes. All these are leaf nodes because their children are null nodes, right? You can consider these as leaf nodes. Okay, 17 goes to the leaf. But you see that now this became what? A 5 node. Once you added 17, it became a 5 node. But you cannot have a 5 node in a 2-4 tree. So that means the size property is violated. You call this as the overflow problem. Overflow, you know, more amount of data that can be stored in a node. Overflow. I mean, you can also hit underflow problem. We will see that later in delete. But this is the overflow problem. More amount of information in a particular node than what can be accommodated. So the size property is violated. So what do? You fix it. So how do you fix it? You use something called a split operation. It can be fixed via a split operation. What is a split operation? So I will give you an analogy, right? So suppose you have, let's think about this. You might have seen beans, right? there are, I mean, various types of beans. One type of beans is like this. And you can split the beans. What happens? So when you split here, so the layer will be out and the bean will spill out from here. The same exact operation will be applied here. This is called split. See, 13, 14, 15, 17. Assume that this is like a bean. You split that, and 15 is a bean that jumps out to its parent. Right? This is the third value. The third value goes to the parent. Okay, once it goes to the parent, what happens? Look at this. You split at this point, right? 13 and 14 will become a separate node. 17 will become a separate node. Look at this. Now you see that size property is fixed at this at this node. That's fixed. However, now the size property is violated at its parent node. So what do?
Professor,
Yes.
here we violate another rule, right? You have 5 children.
Right. So size property is violated here. So what do? What do?
You should
You just
Probably-
split up level.
Again, split. See, we encountered the overflow problem. Size property was violated. We said it can be fixed using a split operation, and we split that node. In this process, what happens is this violation went to the parent node. So we recursively apply the same procedure until size property is violated throughout the tree. Okay, so here there is an overflow problem. Size property is violated. So what do? Again,
Professor, can I just ask a quick question?
yes.
Sorry, when we're splitting and we're moving them up, are we intentionally choosing a key that's in the middle as opposed to a key that's on the end? Like, why didn't we split and push 17 up?
Right. So, I mean, that's the rule. So the rule is we always take the third node and we
The
push it.
third node.
I mean,
Okay.
right? So that would be the best thing to do.
Okay. Okay. Thanks.
I mean, we could have a rule that pushes the second element. That's not a problem at all.
But whichever one we do, we just always do the same one. Okay.
Correct. So, I mean, think
Okay,
about
thank you.
this. So 5, 10, 15. If this moves up, I mean, there is no use, right? It doesn't break into
Right.
two parts. But you want to use one of the middle nodes. I mean, one could have chosen
Okay,
10
okay.
or 12. We fixed the rule that we will always split at the third node.
Because
Okay.
if-
Okay. Thank you.
If you
So,
move the right up, then everything to the right will be disconnected.
right.
Correct. Okay. I see it. Right. Okay.
Okay. So after the split operation at this parent node, what do we find? 12 moves up. 5, 10 becomes its own node.
Interesting.
15 becomes its own node. I mean, look at the beauty of this. Now the size property is satisfied at every level. And the depth property is definitely satisfied. No problem. Right?
Mm.
So after the insert operation, we did some balancing act. See, this shows that the height, right? The height is still what? We can prove that the height is still log n. And you can still do a search like our binary search, right? I mean, similar to a variant of binary search. So you want to make sure that the size and depth properties are always satisfied. If they are not satisfied, what do? You try to fix them. So when we hit the overflow problem, how did we fix them? Split operation. This is the most important operation here, split, right? There is nothing else in inside. Okay, so here is the idea, right? So whenever you encounter, or after adding a value, you get a 5 node. What do? You split. This is the third value, third key, right? That third key goes up, right? So K3 goes here. Now this becomes H1, K3, H2. This becomes a separate node like this, K1, K2. This becomes a separate node, K4. Now there is no violation of the size property here. Maybe there is a violation here that we recursively take care of, right? We recursively keep splitting until, right, everything is fixed. Okay. Now let's understand by solving some examples here. Suppose you want to construct a 2, 4 tree by keep inserting a lot of values. Okay, insert 4. What do you get? You get this. Insert 6, simple. Insert 12, simple. Insert 15, okay. But here you got a 5 node. Size property is violated. So what do? Pick the third key and pop that out. So 12 goes up, 4, 6 becomes a separate node, and 15 becomes a separate node, right? So at the end of this insert, you get something like this. Okay, now let's insert 3, and then we will insert 5. So when you insert 3, where does it go? So 3 is to the left of 12, so it goes here. You insert 3, fine. No problem, right? No violation of any property here. Okay, next, let's insert 5. So 5 is to the left of 12, and it goes and sits in the middle of 4 and 6. You see that now this became a 5 node. Size property is violated here in this node. So what do? Pick the third element and split. So 5 goes to the top. So 3, 4 becomes a separate node, 6 becomes a separate node, 5 goes to the top, right? And what do you get? You get this tree. See, after every insert, we are still getting that 2, 4 tree, right? We are solving that overflow problem using the split operation. And if we have to use multiple split operations, we will. Okay, next we will insert 10. If you insert 10, what happens? See, 10 is between 5 and 12. So it should go to the middle child and sits here. Okay, no problem here, right? So all properties are satisfied. Next, let's insert 8. 8 is between 5 and 12, goes to the middle child, and it is between 6 and 10, and it sits in between 6 and 10. No problem. All the properties are satisfied. Okay.
Professor, can I ask you another question?
Yes.
Can you go back a slide to insert 5?
Yeah, here.
So in the last, where you're popping 5 into the above node to 5 and 12, you're splitting 3, 4, and 6, right? That's the whole split operation. But if you were to put the 5 in the top node and not split 3, 4, and 6, you wouldn't be violating any properties.
Okay, repeat again.
So what I'm saying is when you put 5 between the 4 and the 6, you're now violating the property, right?
Mm-hmm.
But if you were to pop the 5 and put it in the above next to the 12
Mm-hmm.
and keep 3, 4, and 6 on its own, the way it originally
Oh, I
was.
see, I see. Yeah, I mean, that's a very good point, right? See, what you're saying is, why don't we just keep something like this? 3, 4, 6, right here, and 5, 12 here, and 15 here, right? Is this what you're
Right. Yes. Sorry, I was muted. Yeah, that's what I'm saying.
This is a very good question. I mean, why are we split? Why do we need to split? Well, I mean, why can't we just have this? So the rule is that, so if we have a rule, we need to use that everywhere. See, if you can theoretically prove that not splitting works, yeah, that's another way to implement the sort operation. But you need to theoretically prove that I mean, whenever you face this situation, if you do this, you're still going to satisfy all the properties.
Gotcha.
Right?
Yeah.
See, any logic works if and only if you can rigorously prove it.
Okay.
I
Right?
think it works, but there is a drawback of that. So if you insert 5 to 12, then you have to reorganize your 3, 4, 6. That's probably a little bit more than you have the what is called the recursive call.
No, at least in this example, it makes sense, right? But you want to rigorously prove that if I keep doing it, right, for arbitrary operation, there is no problem.
No, I understand. No, I understand what he's saying. If you do what I said, right?
Mhm.
6 is between 5 and 12. So that should be a child on its own in the middle. That's what that's a
Yes.
good point.
Oh,
Exactly,
you're
yeah.
right.
Yeah,
That
you're
is
right,
true. That is
Edward.
true. That is true.
Yeah.
That is true. So
Right.
that cannot happen.
Right. That's a good
That
point.
is true.
Thank you.
That is true. Right? Okay, that's a very good point. That's a very good point. Yes. But yeah, as I said, see, this is not the only logic, right? Maybe there are 20, 30 other types of logic also that works, right? So what I'm saying is any logic that you can come up with, you need to theoretically prove that it works, right? If you can show that, yes, you can potentially come up with another, I mean, logic to implement the same 2, 4 trees or a complete different balancer tree altogether, right? But make sure you're satisfying all those constraints. Yes, so I think as Edward said, it violates that. So which constraint is that? The ordering of items.
Yes.
Right? Good.
But then in that case, wouldn't you just move the 6 to its own node, like in between the 5 and the 12?
Yeah. As I said again, right? So do not look at just 1 or 2 examples. Because having a rule requires a very solid, rigorous proof, right? So, I mean, if you look at a particular example, it might look like thousands of logic should work, but so those examples are unimportant, right? So think about if you can rigorously prove it. Okay. So here, instead of third element, we can pop the second element, right? You can have that rule and it can still work. That is easy because of symmetry, you can prove it. But other types of logic, there might be other constraints, right? Okay, let's move to delete operation, which is more complicated, much more complicated. And see, I can ask questions related to insert. I can give you a series of, say, 50 numbers. You want to keep inserting them and you want to build the trees. But I will never ask a question related to delete operation, simulating delete, because this is slightly complicated. Okay, so we'll try to analyze what happens in this case. So this is the logic. Suppose you want to delete a node. If it does not exist, fine. If it exists, if the node exists, then how do you delete is the question, right? Okay, so to understand this logic, see, there are so many things, so many concepts here. Let's define some terms and concepts, and later we will use these terms and concepts in the different cases. And these different cases will use a lot of operations: swap operation, transfer operation, fuse merge operation, right? It gets complicated. So let's try to understand these terms. Suppose NE represents a node with empty children. Okay, empty children. N not E represents node with non-empty children. Okay, what do you mean by empty children? It is like this. See, square box means empty children. Non-empty children might be something like this. Dot, 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 right? Okay, this is N not E. This is N E. Okay, next. Suppose S34 means you have NE. Suppose you have a node NE, and the immediate sibling of NE is a 3 node or a 4 node. Suppose you have NE here, and the immediate sibling of it, you know what is the meaning of sibling, right? Another child of the same parent, that's the sibling. Okay, so that has to be either a 3 node or a 4 node. In that case, we will call that node as S34. So immediate sibling of any, if it is a 2 node, we will write it as S2. So it can only be this, right? S2 or S3 or S4. But we will combine S3 and S4 as S34. Okay, what else? P is equal to parent of NE. If this is NE, let's call this as P, parent. Okay, so these are the terms we will need. What else? Another important point. Deletion of a node with non-empty children can always be reduced to deletion of a node with empty children. Why is this important? Right? Why is this important? So what do you mean by NE? NE is a leaf node. What is N not E? N not E is a non-leaf node. That means an internal node. Deleting an internal node, you know, is complicated from BST experience, right? It's already complicated, very complicated. Okay, so this is a beautiful idea. So what this says is that you can delete or deletion of a non-leaf node can always be reduced. Reduction, this is called reduction. Beautiful process called reduction. Can be reduced to a deletion of a leaf node, right, in one operation. And why is that significant? Because we will have logic to delete NE. So deletion of N not E can also be reduced to this in one operation. Then you can apply the logic of deletion of N, right? Okay, great. Now let's see all the cases. So you want to delete a node. Suppose that is a node with non-empty children. It is an internal node, internal node, non-leaf node. So what do? This is the internal node. What we do with the NE predecessor. So what we do is we find the predecessor. So this is not empty. Suppose you want to delete this. We find the predecessor of this node, which is a leaf node, predecessor of this node, which is a leaf node, right? And we swap these 2 nodes, right? And then delete. Okay, so this is one idea, right? This is one case. Okay, what are the other cases? Now, these are the other cases. You want to delete a leaf node and it has a sibling that is a 3 node or a 4 node. You want to delete a leaf node that does not have a sibling which is a 3 node or 4 node, right? These are the only two cases, right? Okay, so if there is a sibling S34, then what do you do? Transfer, okay, let's write it like this. Suppose this is NE, this is the leaf node, and this is S34. Okay, so transfer a child and a key from S34 to parent and a key from parent to this node, right? That's how delete works. So we will see an example, right? I'm just giving you the concepts here, then we will see the example. So you want to transfer one value from S34 to parent and one value from parent to any. Okay, so that is this case. What is the other case? Any and S34 does not exist. If this does not exist, there will be S2. So what you do is, let me erase this. Suppose this is NE, suppose this is P, and suppose this is S2. S34 does not exist, right? There is S2. What happens here? You merge and fuse these two. You combine these two, merge or fusing NE with S2 to get NE dash, right? So if there is a 3 or 4 node, the data flows from it to parent and parent to that node. If there is a S2 node, then you fuse or merge, okay? And then move a key from P to NE. So we will see an example, 1 or 2 examples. Okay, so here is one example. Let's see, delete 4. You want to delete 4. So you are deleting NE, right? This is a leaf node. 4 is the leaf node. Okay, so you want to delete this. So if you delete this, you hit the underflow problem. Underflow problem. So size property is violated. If size property is violated, what do you do? Now look at this. The sibling of 4 was this really, right? And this is a 3 node. I mean, we call this as a S34 node, right? It is the sibling of, this node, which is a 3 node or a 4 node. So what is the logic? What transfer operation? You move one key from it to parent and you move a key from parent to that particular node. So that's the idea. See, you cannot push 6 here, right? It violates all that less than, greater than sign. See, because 6 is greater than 5. 5 was here, 6 was here. 6 is greater than 5. So you cannot push 6 to the left node directly. It violates all those properties, right? So you move 6 to the parent and you move parent 5, parent key 5 to this node where you encountered that underflow problem. So this covers one case, right? How did this work? Transfer operation. This is called the transfer operation. You deleted the key from a leaf node. If you encounter an underflow problem, then how do you fix it? Right? Make sure there is a sibling with a 3 node or a 4 node. In that case, push one key from this 3 node to parent and one key from parent to that node where the underflow problem was encountered. Right? So this is one case. And why we couldn't push 6 directly to this node? It violates the less than symbol, right? 6 is greater than 5. So 6 cannot be to the left child of 5. Hence, we had to use this type of transfer operation. Okay. Next. Suppose you want to delete 12. Let's consider a super complicated case. You want to delete 12. Okay, if you want to delete 12, let's find the predecessor of 12. What is the predecessor of 12? It's 11. 11 is the predecessor of 12, right? What is 11? 11 is a leaf node, right? So we delete that 12. 11 moves to the root node. See, we delete that 12. 11 moves to the root node. If 11 moves to the root node, what happens? This will become empty. If this becomes empty, it is an underflow problem. See, in insert operation, we were encountering overflow problem. In delete, we are encountering underflow problem. Right? Okay. So if we face an underflow problem, what do? We check different cases. We check if there is a sibling of this node, which is a 3 node or 4 node. Oops, we did not find any sibling that is a 3 node or 4 node. So we cannot use a transfer operation, right? We cannot do a transfer operation. What else can we do? So we have an S2. There is a 2 node, right? We don't have a 3 node or 4 node. So we cannot use the transfer operation, but there is S2. When you have S2, what did we say earlier? We can use a merge operation or a fusion operation. S2 means what? There is only one key. When you have only one key, you want to merge them. You want to fuse them to make bigger, more keys, right? But here there is only one. This is anyway empty. With one, it's only one value, right? So now let's see. See, when you fuse 8 and this empty node, what do you get? It is 8, right? 8 is larger than what? 8 is larger than 6, but it is less than 10. Now think about it. If we fuse these two nodes, think about what happens to the parent. This becomes a 2 node because this is one child node. This is another child node. So this becomes a 2 node. The parent becomes a 2 node. If the parent becomes a 2 node, it should have only one key. But currently it has 2 keys. So what do? You push, right? You push one of those extra keys, 10 here, to the fused or merged node. See, if 10 was here, it doesn't make sense, right? See, suppose 10 was here, it doesn't make sense. This is a 2 node, it has 2 keys. It doesn't make sense. So you have to push a value. Can you push 6 here? Can you push 6 instead of 10?
Yes, you can. You push 6 to the left, right?
So this will be 10. Suppose
But 8
this
is
is
not
6.
good. No.
Why not?
Evaluate
Because-
the ones.
Right. You want to
You
make
don't have
sure
right chosen.
all the values here are greater than the parent. So you cannot push arbitrary value. So you need to compare, right? Which ones you can push. You cannot push 6 here. You have to push 10. Okay. Now all the values here are greater than 6. All the values here are less than 6. Okay. So this is the fuse operation. So what did we see till now? Okay. So if you're deleting 13, it is simple, right? I mean, so if there are a lot of keys in a leaf node, deletion is dead easy. But if there is only one value or something like that, you can hit the underflow problem. And we covered a lot of cases. Swapping with the predecessor. Where did we cover swapping? Suppose you wanted to delete 12. The predecessor of 12 is 11. And you swap 11 and 12, right? Or you can say, I'm moving 11 to 12 and 11 becomes empty, right? So you can consider that as the swap operation. Okay, next, transfer. Where did we see transfer? So transfer we saw here. We encountered an underflow problem and it had a S34 sibling. When you have an S34 sibling, you must do the transfer operation. Okay, and this was logical, right? We couldn't shorten it. We couldn't directly move a value from sibling to that node because it violated all that inequalities. So we had to push one key to parent and one key from parent to that node. Okay, and then we covered the fuse or merge operation. And when is this true? Suppose you are deleting from a node. So here, see, we found this as part of another operation actually. So when we hit the underflow problem, we saw that it did not have any siblings which were 3 or 4 nodes. All these are 2 nodes. This is a 2 node. This is a 2 node. So we cannot use that transfer operation because we had a 2 node, right? Immediate sibling means this. I mean, this is also a sibling. But what is the meaning of immediate sibling? This is the immediate sibling. 5 is not the immediate sibling, right? First, you need to see 8, not 5. So you want to look for immediate sibling. 8 was the immediate sibling. And then we did a fuse operation. Fuse operation, combined them. When we combined them, that becomes 1 node. And the status of the parent changes because it has 1 node less. When it has 1 node less, you need to reduce the number of keys also. So you need to push 1 key to the child. Okay. So this covers all the cases here. Anyway, so go over these details again. This is slightly complicated, but I will not ask, examples in the exams related to this, but I can ask questions related to insert, right? I can give, 15 values and say, insert this one after the other and construct a tree. So as you can see, every node has constant number of keys, right? Constant number. What? So three keys, right? At most 3 keys, not more than that. So constant number of keys. And what else? The branch factor is at most what? 3 or 4, right? 4. So you can show that the height will be log n. Whatever might be the tree, the height will be log n. Even in the worst case, if you keep adding 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So try to create a 2-4 tree using these numbers, right? It will show you that the height is still O of log n. I mean, you can say theta of log n, right? Height is still theta of log n. So when you apply these operations, you will see that in the worst case, it's log n everywhere. Make sense?
And Professor,
Yes.
we're implementing this with a linked list, right?
Linked list is, you mean linked tree?
Yeah. Sorry, a linked tree.
Yes,
How are we
yes, linked
yeah.
tree. Yes.
Okay.
Linked tree, correct. Okay, let's move to B trees. So that's the end of balanced search trees, right? I don't think we will have enough time, but I'll try to cover a few slides at least. So B trees. What are B trees? B trees is the generalization of, you can say, 2-4 trees, right? Generalization of that is AB trees, and one case of AB trees is B trees. So before that, before understanding, we will not go into the rock bottom details of B trees and so on. So we will do some, coverage of very high level concepts and applications and motivation and all that stuff here. Okay. Computer memory. Probably you know this already. Network storage, external memory, internal memory, caches, registers, CPU. Okay, so this is a one processor machine architecture. As you go from bottom to top, the memory will be bigger and bigger and bigger. As you go from top to bottom here, the speed of accessing information, right, is faster and faster and faster. So as you can see, these two are inversely proportional. You can theoretically prove that you cannot have a bigger memory and a faster memory simultaneously, right? So this is the problem. So due to this problem, we have this hierarchy of memories. Why we cannot have one big chunk of memory that is super fast? Because of, right? I mean, you can theoretically prove this problem. Okay, so it's impossible to have a bigger and faster memory simultaneously. Cache efficient algorithms. So here is your interview question. I will give you a file, which is a 1 GB or say 10 GB file of natural numbers. You want to sort it efficiently. Which sorting algorithm do you use? You can say, I want to use quicksort. Quicksort is the fastest algorithm, right? Or merge sort. Merge sort has worst case n log n. No, those are not the best sorting algorithms when you have a big file. Of course, you know, all your packages, right? Sort function in programming languages, by default, they use either quicksort or a variant of quicksort. Quicksort is considered as the fastest RAM algorithm. What do you mean by a RAM algorithm? That means if your memory fits into the RAM, then it is a solid, you know, very fast algorithm in practice. Right? Theoretically, it has the worst case of n squared, but you know, in most cases, average case, most practical examples, it runs pretty fast. Hence, that is what is typically implemented. Okay, but not quicksort when you are dealing with large files. Why? I mean, how? So what is that algorithm that beats even quicksort or normal merge sort, right, when you have big files? So these are external memory algorithms. External memory algorithms means they reduce communication. See, whenever you have whenever you are saving or storing a file. So let me show this one. Suppose this is 10 GB of file. And suppose your RAM is, say, 512 MB or whatever, right? And this is your CPU. Any algorithm is requires the communication of data, right? Data from, say, here or here to here, or if it is external memory related problem, data from external memory, say hard disk, right? When we say external memory, it can mean hard disk or something else also. Hard disk to here, right? First, it has to come from hard disk to RAM, RAM to L3, L3 to L2 cache, L2 cache to L1 cache, L1 cache to registers, registers to CPU, right? So this is how that there is a lot of data movement. You can try this out. Suppose you want to copy a movie, right, from your hard disk to anywhere. It is damn slow. even a 700 MB movie can be damn slow. Why? Because accessing, right, a location in an external memory is super slow. So this is where you want to minimize communication. So all your quicksort and merge sort are fast in computation, but when you run them here, they are not minimizing communication. They are computation efficient algorithms, but communication inefficient algorithms. And many a times communication takes more time than computations. So try this out. So try to access something in your hard disk, create a file on your hard disk and access some numbers from your programming language. You will see that just accessing a few numbers, whereas even one number is much slower than probably 1,000 multiplications, right? So what does that tell you? It tells you that you want to construct, devise, design algorithms that are not just computation efficient, but also communication efficient, that reduce the data movement. Okay, so the best algorithm here would be, I mean, there is something called external memory merge sort. Okay, so we will not cover this out of scope, but I just wanted to motivate you here on the communication. An algorithm that makes good use of cache, right? Cache, you can say memory or something, is called cache efficient algorithms. And you want to come up with cache efficient data structures and algorithms to reduce communication. And you know why, right? Whenever the data is big, communication is more expensive than computation, right? Okay, so there are two types of cache data locality. One is spatial data locality and temporal data locality. Oh, I think we are out of time here, right? So I will stop here. We will continue in the next session, right? I'll stop here.
Really quick question, Professor.
Yes.
The test is a week from